Platform. In this module, we'll examine the infrastructure behind Google Cloud Platform, or GCP, which was originally built to power Google's own applications and is now available to you. Then, we'll cover the big data and ML products that are built on top of that infrastructure and when you should choose which products for your solution architecture. After that, my favorite part of this course, learning from other customers who are using Google Cloud by exploring their use cases and getting inspired to solve similar challenges for your own teams and projects. You will learn where you can look up reference case studies of GCP customers by industry or by product. And then you'll examine their solution architecture in a short activity. Building the right team structure is critical to solving these big data challenges. We'll explore the different types of roles and personas for building a successful big data team within your organization. Consider for a second the impact that Google Search has on our daily lives with timely and relevant responses. Now think of other Google products: Gmail, Google Maps, Chrome, YouTube, Android, Play, Drive. Each of these products has over 1 billion monthly users. Google has had to develop the infrastructure to ingest, manage, and serve all the data from these applications, and to do so with a growing user base and data requirements that are constantly evolving. 7 products with 1 billion users. Actually, there's an 8th Google product that has 1 billion end users. Google Cloud, except that it's your users. The end users served by Google Cloud customers such as Home Depot and Spotify, Twitter and New York Times, Colgate-Palmolive and Gojek. Let's look at the building blocks behind Google's big data infrastructure and how you can leverage it with Google Cloud. There are 4 fundamental aspects of Google's core infrastructure and a top layer of products and services that you will interact with most often. The base layer that covers all of Google's applications, and therefore Google Cloud's too, is security. On top of that are compute, storage, and networking. These allow you to process, store, and deliver business-changing insights, data pipelines, and machine learning models. Finally, while running your big data applications on bare metal virtual machines is possible, Google has developed the top layer of big data and ML products to abstract away a lot of the hard work of managing and scaling that infrastructure for you. A growing data organization like yours will need lots of compute power to run big data jobs, especially as you design for the future so that you can outpace the growth in new users and data for the next decade. Let's start with an example illustrating how Google uses its own compute power. Google Photos has recently been introducing smart features like this one for automatic video stabilization, for when the camera is shaky, as you see here on the left. What data sources do you think are needed as inputs to the model? Well, you need the video data itself, which is essentially lots of individual images called frames ordered by timestamps. But we also need more contextual data than just the video itself, right? Absolutely. We need time series data on the camera's position and orientation from the onboard gyroscope and motion on the camera lens. So, how much video data are we talking about for the Google Photos ML model to compute and stabilize these videos? If you consider the total number of floating point values representing a single frame of high-res video, it's a product of the number of channel layers multiplied by the area of each layer, which with modern cameras can easily be in the millions. An 8 megapixel camera creates images of 8 million pixels each, approximately. Multiply that by 3 channel layers, and you get over 23 million data points per image frame. And there are 30 frames per second of video. And you can quickly see how a short video becomes over 1 billion data points to feed into the model. And from 2018 estimates, roughly 1.2 billion photos and videos are uploaded to the Google Photos service every day. That is 13 plus petabytes of photo data in total. For YouTube, which also has machine learning models for video stabilization and other models for automatically transcribing audio, you're looking at over 400 hours of video uploaded every minute. That's 60 petabytes every hour. But it's not just about the size of each video in pixels. The Google Photos team needed to develop, train, and serve a high-performing machine learning model on millions of videos to ensure that the model is accurate. That's the training dataset for this one feature. Just as your laptop hardware may not be powerful enough to process a big data job for your organization, a phone's hardware is not powerful enough to train sophisticated machine learning models. Google trains its production machine learning models on its vast network of data centers and then deploys smaller trained versions of these models to the hardware on your phone for predictions on new video. A common theme throughout this course is that when Google makes breakthroughs in AI research, it continues to invest in new ways to expose these as fully trained models for everyone. You can therefore leverage Google's AI research with pre-trained AI building blocks. For example, if you're a company producing movie trailers and quickly want to detect labels and objects in thousands of these movie trailers to build a movie recommendation system, you could use a Cloud Video Intelligence API. You could use that API instead of building and training your own custom model. There are other fully trained models for language and for conversation too. You will learn and practice using these AI building blocks later in this course. But getting back to the Google Photos machine learning story, running that many sophisticated ML models on large structured and unstructured datasets for Google's own products required a massive investment in computing power. That's why Wired says, this is what makes Google Google. Its physical network, its thousands of fiber miles, and those many thousands of servers that in aggregate add up to the mother of all clouds. In essence, Google has been doing distributed computing for over 10 years for its own applications, and now has made that compute power available to you through Google Cloud. But simply scaling the raw number of servers in Google's data centers isn't enough. Here's an interesting rough calculation by Jeff Dean, who leads Google's AI division. He realized years ago that if everybody wanted to use voice search on their phones and used it for only 3 minutes, we would need to double our computing power. Historically, compute problems like this could be addressed through Moore's Law. Moore's Law was a trend in computing hardware that described the rate at which computing power doubled. For years, computing power was growing so rapidly that you could simply wait for it to catch up to the size of your problem. Although computing power was growing rapidly even as recently as 8 years ago, In the past few years, growth has slowed dramatically as manufacturers run up against fundamental physics limits. Compute performance has hit a plateau. One solution is to limit the power consumption of a chip. And you can do that by building application-specific chips or ASICs. And one kind of application is machine learning. Google's designed new types of hardware specifically for machine learning. The Tensor Processing Unit, or TPU, is an ASIC specifically optimized for ML, and it has more memory and a faster processor for ML workloads than traditional CPUs or GPUs. Google has been working on the TPU for several years and has made it available to other businesses like yours through Google Cloud for really big and challenging machine learning problems. One such business that uses TPUs is eBay. They use cloud TPU pods to deliver faster inferences of predictions, faster inferences to their users by a factor of 10. That's a 10x speed up. The decrease in model training time has also led to faster model experimentation. ML model training and feature engineering is one of the most time-consuming parts of any machine learning project. eBay's VP of New Product Development remarked that the additional memory of the TPU pods enabled them to improve their turnaround time and iterate faster. One last example of compute power at Google and an inside look at our culture of thinking 10x is how our teams used machine learning to boost Google's own data center efficiency. The potential impact for machine learning was there, considering the number of data centers that Google has to keep cooled and powered, and we were already collecting streaming sensor data for our existing monitoring platforms. Engineers at Alphabet's DeepMind saw this as an opportunity to ingest that sensor data and train a machine learning model to optimize cooling better than existing systems could. The model they implemented reduced the cooling energy by 40% and boosted the overall power effectiveness by 15%. I find this example particularly inspirational because it's a machine learning model trained on machine learning specialized hardware in a data center, telling the data center how hot it can run the machine learning specialized that the model is training on. Powerful inception level stuff. Later in the course, you will see a demo on how you can set up a streaming data ingestion pipeline for your own IoT devices in less than an hour. So in this demo, I'm going to be showing you how to spin up a Compute Engine instance, run some software on it, copy files from that Compute Engine instance to cloud storage, and publish those files to make them public. The use case that we're going to be doing is to plot earthquake activity that happened in the previous week. And this data comes from USGS. So let me go ahead and go to cloud.google.com. So I'm starting on cloud.google.com, and I'll go to the Compute Engine part of it, go to VM instances, and create a VM. So I'll click Create here, and at this point, I'm creating a new virtual machine. Let's call it an Earthquake VM. We can call it whatever we want. We can choose where in the world we want it. I happen to be closer to Oregon now, so I'll go ahead and do US West, and I'll pick a zone. I can pick US West B. Let me go ahead and say that I want to use 2 virtual CPUs. As you can see, we can at this point in time go up to about 64 CPUs with about 250 gigs of RAM. Another thing that I can do is I can click Customize and say that I want 18 CPUs and 50 gigs of RAM. Go find me a machine that matches these requirements. But in our case, what we'll do is we'll just go back and we'll pick a pretty small machine. like 1 BPU is probably enough. And then 10 gigs of space is enough, but of course we can change that and we can use a different operating system with the different size of disk if we wanted. And we want to be able to use GSUtil, gcloud, etc. So I will allow full access to all my cloud APIs so that I can write to cloud storage from the VM. And I don't want to directly access the VM through HTTP or HTTPS. So we'll just access it through SSH. So I'll go ahead and create the virtual machine. And at this point, the virtual machine is getting created. Let's wait a few seconds. And once the VM is up, we should be able to SSH into it. So there it is. Here's my VM. And at this point, this is a bare bones virtual machine that I'm SSHing into. This virtual machine, clear ls, so it doesn't have anything on it. In fact, it doesn't have even very basic software like Git. So if I were to type Git here, it says Git is not found. So I need to install Git. Good thing is we can do that, right? I have root access. And so what I can do is I can do sudo, which gives me root access, apt-get install Git. Okay. And it says, do you want to continue? Yes, I do. And this now installs Git, which is a way to access my source code repository, which contains everything else that I need. So I will go ahead and do git clone, https www.github.com, Google Cloud Platform. So this now gets the data from GitHub, gets all of the data that I need, including the files. And now if I do ls, I have my repository. And in this case, this is part of the files for this course. And so we can go into BDML fundamentals. And there is the Earthquake VM. I'll go into the Earthquake VM and look at what files are present. Turns out that I have an HTML file already. I have some a shell script to ingest data. I can do less ingest.sh. And this basically goes ahead and removes an existing earthquakes.csv and does a wget, which is a way to download data over HTTP from earthquake.usgs.gov and saves it as earthquakes.csv. So that's what ingest.sh does. But in order, then I also have transform.py. And transform.py basically is some Python code that uses matplotlib to go ahead and parse the earthquake data from USGS and put it on an earth map, creates a PNG out of it. So this particular file can be run to go ahead and process a weekly data from the USGS. It goes ahead and gets 1 week of data from USGS and creates earthquakes.png. In order to do that, though, I need to have some software installed, and the software that I need, it's all listed in the installed missing.sh. So I need to basically get a bunch of different Python libraries. So let me go ahead and first run install missing.sh. This goes ahead and downloads and installs all of the Python packages that I need. As you can see, working with a virtual machine on the cloud is like working with any other Unix machine. In this case, because I created a Debian machine, I get a Unix machine, and that's the Unix machine that I'm working with. At this point, it has all the Python packages that I want. We can go ahead and say ingest.sh, and it will go ahead and download an earthquakes.csv. You can see that there's an earthquakes.csv now that's been created. And if we were to do head shows the first few lines of the file. It turns out that currently there has been an earthquake in California, and there has been another earthquake in Alaska, and so on, right? So let's go ahead. And so there's 93 kilometers east-northeast of Cape Yakataga, Alaska at the time that I'm recording this demo. So there's a bunch of earthquakes. We've gotten the data. But looking at a CSV file is not very interesting. Let's go ahead and create an image out of it. In order to do that, I will run transform.py. So transform.py is essentially getting the earthquake data, converting an image. And notice at this point, there's no image, but now if I do ls_star.png, I now have an earthquakes.png. So let's go ahead and now put it onto the cloud. We want to get rid of this virtual machine. The whole idea is compute and storage are separate. So we've done the compute, we have some files, let's copy them off the machine into cloud storage so that we can delete the machine. Right? So let's go and create a cloud storage bucket. The way to do that is, again, go down here, and last time we did compute engine, this time we're going to do storage. So we'll go to storage browser and say that we want to create a bucket. Okay, so let's go ahead. I already created this bucket. Let me just delete that. I don't need that bucket. Let's say that I want to create a bucket, and I have to give my bucket a unique name. So let's say that I want to give the bucket the name earthquake, but the bucket name is already in use. A bucket name has to be globally unique. So I can say earthquake 2019, and I have it, right? So there is nobody else who's created a bucket of this name. If you can't come up with a unique name, try using a project name, right? This project name is also globally unique, and in many cases, that might work as well. An easy way to do that is we could go down to the home menu, and there is a project name. I can copy the project name, go back to the storage thing and say, can I create a bucket of that name? Yep, I can. So that also works. So I can create something with this particular name as my bucket. Let's make it multi-regional so we can access it from anywhere in the world. And it's going to cost us about 3 cents per gigabyte per month. And we can now choose how to set the permissions. Normally, you want to set permissions, but one object by object, right? But let's go ahead and specify it object by object. So we can go ahead and create the bucket. So now we've created a bucket with this name, and I'll copy that into my thing. And that bucket is now created. We can now come back to this virtual machine, and we can say gsutil ls and the name of the bucket. And it doesn't have anything in it right now. So it should be empty. So it doesn't have anything in it. What we can now do is we have gsutil copy earthquakes.star to the bucket. So at this point, it's copied 3 files. It's copied the CSV file, the HTML file, and the PNG file. And indeed, when we come down here and we say refresh, we should have the 3 files. So hooray. So we have the 3 files. All 3 files currently are not public. So no one can access them except us because we own these files. But from this point onwards, I don't need the virtual machine. So let me just go down to the compute engine and say, hey, that virtual VM instances, select my virtual machine, and I can do one of 2 things. I can stop the virtual machine, in which case it's like pausing the VM. I'll be paying for the disk, but I won't be paying for the storage at all, right? The other thing that I can do, instead of stopping the VM, is that I can delete the VM. Right? So I can go ahead and delete the VM. I don't need it ever again. So stopping is actually a very convenient way. We've installed a bunch of software. We don't want to get rid of the VM, but we don't want to pay for the compute of the VM. So what we could do is we could just stop it. Right? So the VM is no longer running, and we can just say stop. And now the VM is paused. And at this point, right, once that VM is paused, we'll only get charged for that 10 gigs of disk that we had attached to the VM. So a relatively inexpensive way to have a virtual machine sitting around that has all of the software, everything that we have installed on it. If we ever need to run things again, we can come back, restart the VM, and run things. But let's go back to our storage. And you will see that the data here is private. And what we want to do is that we want to make it public. We want to make it accessible from anybody. What we could do is we could go down to the storage. And now we are in the bucket. And we can say that we want to take these 3 files, go to the permissions, okay, right? And we can say that we want to go to the permissions and we want to add members. And we can add a members called all users, okay, and give those users, everybody, storage object viewer. So they will be able to view that particular object. Okay. So now we have our all users, okay, and all users has a storage object viewer on these objects. So now if we go now, we see that these 3 things are public, and Google Cloud helpfully warns us that these 3 things are public. They all have public links associated with them. So we can actually go down here and say, what is a public link? Click on the link, and that is storageapis.googleapis.com. So anybody who comes to this particular link will be able to basically see the earthquakes this week. So this is, at this point, I'm recording it on March 28th. I'm recording it on April 4th. So the week started on March 28th. So I have 7 days of data, and these are the earthquakes that we saw in Alaska, and those are the earthquakes that we saw in California, and you can kind of see the ring of fire with all of these earthquakes that are happening around the coast of the Pacific. But to bottom line, what did we do? We spun up a virtual machine, we carried out processing on it, and then we took those files, we copied them to cloud storage, we were able to stop the VM. VM is no longer running, but the files are still available, and we're able to serve them out. In the demo at the end of the previous section, I copied the ingested and transformed files out of the compute instance into cloud storage. This way, we could stop our compute instance and retain access to the data. While we've discussed the demand for a great amount of computing power for today's big data and ML jobs, we still need a place to store all the data that's generated. As with the demo, this needs to be separate from the compute instances so that we can analyze it, transform it, and feed it into our models. This is one major way that cloud computing differs from desktop computing. Compute and storage are independent. You don't want to think of disks attached to the compute instance as the limit of how much data you can process and store. Getting your data into your solution and transforming it for your purposes should be your first priority. In the roles and team structure discussions that I'll talk about later in this module, I'll talk about the need for data engineers to build data pipelines before you can start building machine learning models from that data. And when the pipeline is built, the job isn't done. Because once the data is in your system, data engineers are still needed to replicate the data, back it up, scale it, remove it as needed, all at scale. Instead of data engineers managing storage infrastructures themselves, data engineers can use Google Cloud Storage, which is a durable global file system. Creating an elastic storage bucket is as simple as using the web UI in console.cloud.google.com or the Google Storage Utility function called gsutil in the command line interface. As an additional level of flexibility, a data engineer can choose what type of storage class they want for their data.
There are 4 storage classes for you to choose from based on your data needs: standard storage, nearline storage, cold line storage, and archive storage. Regardless of which one you choose, All classes have multi-region, dual region, and region location options. So they differ based on the access speed and the cost. Standard storage is the fastest, and archive storage is the least expensive. A good trade-off, for example, is to use nearline storage for data that you might access only monthly. For data analysis workloads, it's common to use a standard storage bucket within a region for staging your data. Why do I say within a region? That's because you need the data to be available to your data processing computing resources. And these will often be within a single region. Co-locating your resources this way maximizes the performance for data-intensive computations and can reduce network charges. Cloud storage buckets are an example of a cloud resource. Let's cover some of the account management logistics that you need in order to use cloud resources.
Starting from the most granular objects, you see that resources, like your cloud storage bucket or compute engine instance, these resources belong to specific projects. Bucket names have to be globally unique, and GCP assigns you a project ID that's globally unique too. And so you can use that project ID as a unique name for your bucket. But what's a project? A project is a base level organizing entity for creating and using resources and services, for managing billing, APIs, and permissions. Zones and regions physically organize the GCP resources you use, whereas projects logically organize them. Projects can be created, managed, deleted, even recovered from accidental deletions. Folders are another logical grouping you can have for collections of projects. Having an organization is required to use folders. But what's an organization? The organization is a root node of the entire GCP hierarchy. While it's not required, an organization is quite useful because it allows you to set policies that apply throughout your enterprise to all the projects and all the folders that are created in your enterprise. Cloud Identity and Access Management, also called IAM or IAM, lets you fine-tune access control to all the GCP resources you use. You define IAM policies that control user access to resources. Remember, if you want to use folders, you must have an organization. Now that you have a Google Cloud Storage bucket created, how do you get your data on the cloud and work with the data once it's there in the bucket? In the demo, I used gsutil commands. Specifically, we can use cp for copy and specify a target bucket location. If we spin up a compute engine instance, the command line tool gsutil is already available, and we can do gsutil copy. On your laptop, you can download the Google Cloud SDK so that you can get gsutil. gsutil uses a familiar Unix command line syntax, so if you know how to use the cp command on Unix, you know how to use gsutil cp. So far, we've looked at compute and we've looked at storage. The third part of Google Cloud infrastructure is networking. Google's high-quality private network, petabit bisectional bandwidth, and edge points of presence are combined using state-of-the-art software-defined networking to deliver a powerful solution. First, the private network. Google has laid thousands of miles of fiber optic cable that crosses oceans with repeaters to amplify optical signals. And as you can see in this amusing GIF, it's shark-proof. Google's data centers around the world are interconnected by this private Google network, which by some publicly available estimates carries as much as 40% of the world's internet traffic every day. This is the largest network of its kind on Earth, and it continues to grow. Second, the petabit bisectional bandwidth. One of the themes we will discuss in this course is a separation of compute and storage. You no longer need to do everything on a single machine or even a single cluster of machines with their own dedicated storage. Why? Well, if you have a fast enough network, you can perform computations on data located elsewhere, like many distributed servers. Google's Jupyter network can deliver enough bandwidth to allow 100,000 machines to communicate amongst each other. So for any machine to communicate with any other machine in the data center at over 10 gigabits per second. This full duplex bandwidth means that locality within the cluster is not important. If every machine can talk to every other machine